Hi, my name is Marshall Lisenby, and this is my Physics 2212 Lab 4 report, bar magnets. The purpose of this lab is to measure the distance-dependent magnetic field of a small bar magnet, as well as compare the observation with prediction for Biot-Savart law of on and off-axis magnetic dipole fields. So the materials for this lab are a phone with magnetometer app, yardstick, tape, bar magnet, and then glow script as our computational model. And the main results for this lab was that we found N to be negative 2.15 and the magnetic dipole moments to be 141.07 amperes squared. Now, for the fundamental physics principles that define this lab, we first have the Biot-Savart law, which relates magnetic field at a point to a small current element, given by the equation shown below. Next, we have the magnetic field of a dipole, and a magnetic dipole is a closed circulation of an electric current system, with the equation given below, with a field that in some ways mimics that we saw with the electric dipoles earlier in this class. And then finally, we have the distance-dependent formula, which is the magnitude of the magnetic field due to a bar magnet falls off with distance. And we can find that with this equation shown below, which is going to be linearized in our data set as seen in that graph next to my head. Now, for the experiment and its actual procedure. First, you start by orienting your phone to be orthogonal to the Earth's magnetic field. And you do this on the yardstick next to the magnet as shown there. And then you find the location of the magnetometer through using tape to isolate the actual spot in the phone where it's located. And you measure distance between magnetometer and bar magnet for on and off axis, where the bar magnet is the system and everything else is the surroundings. And you do this multiple distances to collect a data set for both on and off axis. Now, here is the data for the on-axis part of the experiments with the actual distances and fields on the left, and then the linearized plot of that to the right. And with this data, we were able to determine a value for N and K through the linearized equation, which is shown above my head. Now, using those equations, we can use the relation between those two relations we found earlier in the lab to discover the magnetic dipole moment for this actual experiment. And through plugging in the values that we got in the linearized plot, we were able to find the magnetic dipole moments to be 141.07 amps meters squared. Now, for the off-axis set of the experiment, where instead of having the magnetometer on line with the bar magnet, we put it perpendicular to it, and then find the actual values of the magnetic field there. And in this scenario, we found that the magnetic field's at the average distance of 0.228 meters from the actual axis. For the computational model, we can begin this part of the experiment. And we start by making a function for the magnetic field as well as plugging in our initial values, which is 141.07 amps meters squared from the found data in the actual experiments. And then we can move on to the visual part of the computational model. Now, for the visual part of the model, we can start by also using our average G-perp from experiment part 2 of the experiment. And then we created a visual with 2 on-axis arrows, 4 perpendicular arrows, and then 1 arrow at a 45-degree angle. And what this results in is an average field calculated by the model, which is close to, but a little bit different than our actual found model, which can be due to variation and error. Now, for some assumptions and potential errors within this lab. For the assumptions, we assume that the bar magnet actually acts as a magnetic dipole, and that the magnetic field falls off as distance increases. And then for the errors, we found that possibly other electronic magnetic objects could have skewed the magnetometer data, like a computer or phone being near the actual experiment, as well as the fact that the exact location of that magnetometer was not found precisely, but they're using a sort of an estimate with the tapes and the phones. Now for some observations with this lab report. We found that it was true that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, as well as the fact that as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases, essentially proving true the distance-dependent relationship of a magnetic dipole. What we found to be false was that as the magnetometer moves closer to the magnet, the measured x component of the magnetic field decreases, and the position of the magnetometer has no effect on the measured x component of the magnetic field, both of which go against that distance-dependent relationship that we established in the beginning and found to be true through our data sets. Finally, for some discussion questions. First, what if you hadn't orientated your experiments to compensate for magnetic north, and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? Well, the Earth's magnetic field would interfere with the bar magnet's magnetic field, thus skewing the results, as the angles would be different and offline, causing a different magnetic field to actually affect the data that was found through the magnetometer in the phone, as it always does have an effect on the phone. Second, what if you were to stick 2 identical magnets together, end to end, and run the experiment again? how would you expect your measurements to differ? The magnetic field would double while the direction would stay the same due to the fact that they're still in line but now has twice the magnitude or twice the magnetic field. And that's all for this lab report. Thank you so much for listening.